Hi, in this video I will discuss why oblique reflection of Brownian motion in a generalized parabolic domain leads to either explosion or superdiffusivity. Okay, so this is part 2 of the presentation. In the first part I discussed this result and gave examples to see what the consequences are. But my main aim here is to make it easier to read the proofs in this paper, explain some ideas behind that go into the proof, and say something about the structure of the proof in general. Okay. Now, recall that we are interested in a diffusion in a domain D like this, which lives in Rd plus 1. So this is the x coordinate, the y coordinate is d-dimensional. The domain is defined by this positive function b. And for each x, this slice of the domain is a disk with radius b of x. Okay, the D is a generalized parabolic domain, which means that the derivative of b as x goes to infinity goes to 0, and b is also sublinear because the process needs to interact with the boundary sufficiently to see this phenomenon. Okay, also we have this assumption on the instantaneous variance of the y component of the process, because that y component needs to take me to the boundary sufficiently. So in the limit, this instantaneous variance needs to survive. Okay, you see here I'm just subtracting the instantaneous variance of the x component from the total instantaneous variance, right? That's really the instantaneous variance of the y component. As also the vector field needs to give me some kick in the tangential direction to the boundary, right, in order to go to x, right? This tangential direction is essentially x direction in this sort of context, as discussed in the previous video. Okay, and what's the result? The result says that explosions of such a process really depend on the local integrability of the boundary b at infinity. Okay, so I define this function capital B. It's an increasing function, and its limit b of infinity exists, may be infinite or not. If it is not infinite, then the process is explosive in this strong sense. So the explosion time has finite expectation for any starting point. And if it is not integrable, the boundary, then the process is not explosive from anywhere, and I get this strong law which tells me how asymptotically the norm of z behaves, almost surely, right? Almost surely, it's a strong law, and this leads to this superdiffusive behavior as discussed in the first video. Okay, so how do you prove a result like this? What is the main problem? Well, the main problem is that, the process x is a martingale in the interior, and it gets kick only at the boundary. It's difficult to quantify what happens at the boundary, right? So the state space is not homogeneous. So we homogenize it with a function g. And this function g is x, you see, x, y, z, that's the point in the domain. X is just the first coordinate, perturbed by something not very big. Okay, so this is norm y over b is bounded by 1, and then there's norm y that's left, but norm y is smaller than b, but b is sublinear, right? So this is really asymptotically equal to a constant times x. Okay, so I'm not perturbing it very much, but what I am doing is I'm introducing some curvature in the interior of the domain, and this parameter gamma controls this curvature, right? And so one thing which is important for me is that in the interior, the g of z process will now have a drift, while xt process doesn't have a drift in the interior, right? G of z process will have a drift, and its drift, it's not hard to see, is actually approximately equal to 1 over b of x. Okay, so that's going to be the drift of the g of z. It may be small, but it's there. Okay, and this gamma plays sort of a dual role also, because this curvature not only gives me a drift in the interior, but also modulates, at which angle the level sets of G intersect my boundary, right? So this will control the gradient, the scalar product between the gradient and the vector field, right? But the vector field is assumed, you remember this S0, C0, this is the asymptotic reflection in some sense, right? This phi of z sort of converges in some sense to this vector, right? If you look in the previous slide. Okay, so now what happens? It turns out that key value of gamma is this gamma 0, which is given by this asymptotic reflection, S0, C0. What one does is one applies the integral of the boundary to the function g, okay? So, and then looks at the dynamics of that. So we are still possible explosion, of course. We have a local martingale here. We note that this drift now of this function asymptotically is constant. And it's actually proportional to gamma times sigma squared. Sigma squared is the asymptotic variance of the y component, you remember. And also, importantly, this is this picture of this intersection, the level sets intersecting the boundary, right? Is that for gamma greater than this gamma 0, which is critical gamma, my new function that I see here is negative. And for gamma smaller than gamma 0, this nu is positive. You see, this b, this quantity is always positive. Right, so this nu will determine the sign in front of the local time term. And this is the way into this problem, because this allows me to define a super martingale and a sub martingale, at least intuitively, right? So this psi, you see, if I look at psi and subtract gamma sigma squared plus epsilon t from it, I will get a super martingale, at least when the process x is very far away from the origin, because you see the drift here is asymptotically equal to this, and I've perturbed it a little bit, so I take a little bit larger drift, okay, and I subtract that, so I'll get a super martingale. And when gamma is greater than gamma 0, also this nu will be negative. So this guy will really be pushing me in the direction that I wanted to push me for this to be a super martingale. Likewise, when gamma is smaller than gamma 0, and I subtract this drift minus epsilon, I will get a sub-martingale, okay? At least appropriately localized, okay? So this is still a level of ideas. So these two processes are actually crucial for the analysis that follows. So what are the technicalities involved? You see, so one thing is, in my eta representation of the process, of this process psi, I didn't have control on the coefficients. I only had asymptotic control on the coefficients, but I can get around that by stopping on the left. Okay, so I wait for the process to go far enough. I prove that it goes far enough with good probability, and then I can stop it on the left. Okay, so I stop it on the left. I'll be able to prove super and sub-martingale property. In order to get this m to be a true martingale, I localize on the right, and this localization on the right also what it does is allows me to deal with explosions, because I have to go through a high level before I explode. So if I stop it at a high level, I get a globally defined process. So this is all good. And then, okay, from this intuition, one would suspect, one looks at, it looks at how long does it take my process, my reflected Brownian motion, to reach level R for the first time. Okay, so if this was a Brownian motion, actually of any dimension, this expected value for this time would be a constant, depends on the dimension, times R squared. Okay, that would be the expected amount of time it takes Brownian motion to reach that process. In this case, because this g of z is actually approximately equal to xt, and if you believe this super sub-martingale story, then you can at least formally apply optional stopping theorem to conclude that, you see, this b of r, you see, my process actually is equal to r when I hit r, so b of r, does you remember that psi is b of g of z, right? So b of r, it should be asymptotically equal to the expected value of the first time I reach level r in the x direction, okay, times some constant. And how do I do that? Well, I do this optional stopping theorem, and then I send these guys epsilon to 0, gamma up to gamma 0 to gamma critical, and gamma down to gamma 0 if I'm dealing with the super sub-martingales, and I get something like this. Okay, so this immediately tells you that there is going to be some you see some super diffusive behavior happening here. Because as I was saying earlier, for Brownian motion, this is going to be asymptotically equal to r squared times a constant. But here it's asymptotically equal to this. And this, remember, this b of r is r to 1 plus beta. B of r is capital B of r is the integral of little b of r, and little b of r is roughly r to the beta, right? So integrate that, I get r to the beta plus 1. But 1 plus beta is strictly smaller than 2, right? So this guy is smaller than what the corresponding guy would be for Brownian motion. So this guy, the process grows faster. I mean, this is what you see here. Okay. Similarly, from this sort of intuitive analysis, it is clear that it will be the limiting value b infinity, the integrability of little b of the boundary b at infinity will determine whether this expectation is finite or not. Okay, so this actually can be carried out. These ideas can be made formal. So several steps are required. The first step is a non-quantitative bound that says that this stopping time of hitting r has finite expectation uniformly in z. And that, you know, if I start somewhere and wait until I get far enough, then, and fix epsilon, then the probability that I get back before I go to plus infinity is smaller than epsilon, right? So it's transients, right? And both of these things can be actually established. And from them, we can then prove a proposition like this. Right, so this proposition actually holds. This is the first step in the direction of the proof of the main theorem. Okay? So this tells you that when this happens, I get explosions in the strong sense, and when this doesn't happen, when I have something a boundary which is not locally integrable at infinity, then the expected hitting time of r for large levels r, wherever I start, will grow as the integral b of r. You see, that's the thing. Okay. Now, in order to get a strong law of large numbers, I need to control the martingale part. Of course, I need to make sure that the martingale part is going to vanish in the limit, so I need some quantitative control on the quadratic variation of m. And all these things, I mean, in order to get the strong law, I also need to use this sandwiching idea, right? Why? Between a super and a submartingale, because that allows me to avoid nightmares with local time. I can deal with the local time using the super and submartingale idea just by understanding the sign of the local time term, and not even the sign, but the asymptotic sign of the term in front of the local time, because I can help myself with localizations. Okay? So that's how this theorem is proved. And of course, once you establish the theorem, then looking back, you do get growth asymptotics as a consequence of the theorem of the local time, right? So that's one way of analyzing that. The explosive case is a little bit more technical, but of course it needs to be, it can be analyzed using the same ideas. So the paper, the way it's structured, is that the results are based on general semi-martingale criteria, when semi-martingales even can have jumps and are possibly explosive for so for explosion, non-explosion, and the asymptotics of hitting times of these semi-martingales in R+. Okay, so these results we think will have applications in other settings. Okay, and then of course, then all you do in the reflected Brownian motion case is sort of show that you can apply these theorems. You need to work to show that you can apply these semi-martingale theorems to the context of the reflected Brownian motion in this generalized parabolic domain. Okay, so this leads to another model for anomalous diffusion. Anomalous diffusion is a quantity which is of great interest in physics, of course, but also in mathematics. It's gaining a lot of momentum. It's arising in many areas of not just probability, but also analysis and applied mathematics. And it's got its own AMS classification. It got it in 2020. Now, the closest result to the ones that I've talked about here were done by Pinsky in '09, where he considered normal reflection and sigma equal to the identity. And of course, in that case, it's the recurrence and transience that can only occur, it turns out, and the behavior is at most diffusive. Okay, the behavior is at most diffusive. Now, if one generalizes, if one allows sigma to be more general, so a non-identity covariance matrix, say, then a richer behavior in the generalized parabolic domains can be obtained, going from transience to, I mean, in this in the normal reflection situation, actually just asymptotic normality really matters, because it's the asymptotic behavior that drives everything, as in this oblique reflection case. And you can get anything with asymptotically normal reflection from transience to positive recurrence, and it is also possible to understand the tails of the in the positive recurrent case, the tails of the stationary measure, as well as understand the rate of convergence in total variation to the stationary measure, including, so it's possible to get lower and upper bounds on the total variation, which match, thus obtaining the actual rate. So this is going to be the topic of our forthcoming joint paper with my PhD student Mijatovic A.R. and Andrew Wade, which should be released soon. I hope you enjoyed this video. Thank you for watching.